Okay, so this is just some stuff in the appendix that will occur. It's not, you don't really have to know it that deeply, but first thing is about the Riemann integral. So there's this definition of integrability. What does integrability mean? There are multiple ways of doing this. Here is one way. So a bounded real value function f on some interval is called Riemann integrable. It's called Riemann integrable if there exists, if whatever epsilon you're given, there exists a partition P such that the upper sum on P minus the lower sum on P is smaller than epsilon. Okay, so this is one way of defining it. What it's saying is that you have some function, right? You have some function, and so just to remind people what these things are. A partition is some way of dividing up this interval, right? So you divide it into subintervals. Okay, so here is one partition. Let's call it P. Okay. This UPF means the upper sum on that partition, right? So it means that you take the partition and then you take the supremum of the function on that partition, right? So here, over this you take each interval and then you take the supremum on that interval, right? So over this interval, here's the supremum, right? And you take that and you multiply that value by the width of the interval, right? And so you get this area. And you do that for every interval. So in this one, the supremum occurs here, right? Occurs here, occurs here, right? Occurs here, right? Occurs here, occurs here, right? So this would be the sum of these values, right? The sum of these, right? The supremum over the interval, the supremum of the function over that interval, times the width of the interval, over their partition. This would be the upper sum. Okay, and you don't have to copy this down too carefully. Just understand, right? Like, take the supremums. That's the upper sum of the function over the partition, right? And then the lower sum would be, of course, you take the infimum. Instead of taking the supremum, you take the infimums, right? And that would be the lower sum, right? And so what it's saying is that if no matter what epsilon you're given, you can find a partition that's fine enough that the upper sum and the lower sum are that close to each other. Right? In other words, you can make the upper sums and lower sums as close as you want. Right? In that case, your function is called Riemann integrable. For an example of a function that's not Riemann integrable, kind of the standard one is you take the characteristic function of, say, Q. Right? So it's 1 if your function is rational and 0 if your function is irrational. Right? So let's say we take that on 0, 1. Right? So for every rational number, you have a value of 1. For every irrational number, you have a value of 0. Right? And that's not Riemann integrable because when you... Is it okay? I'm going too fast? Good, right? Okay, good. That's not, right? That's not going to be Riemann integrable because your upper sums whatever partition you take, when you take the supremum over that over each interval, well, you're always going to get a height of 1, right? So your upper sums are always going to look like this, right? Your upper sums are always going to have a height of 1, right? And when you add it all together, right, you're going to get the upper sum over that partition is always going to be 1, and the lower sum, right? The infimum over each interval is always going to be 0, right? Right. So we can't make, no matter how finely we divide this stuff, right? No matter how finely we take a partition down here, we can't get the upper and lower sums close to each other, right? So, okay. So just as a kind of quick reminder of what Riemann integrable means, and then definition, if f is integrable, f for f integrable on AB, then we define the definite integral as the infimum of the upper sums, which is going to equal the supremum of the lower sums. Okay, so you take the upper sums and you take the infimum of the upper sums. Right. So as you take finer and finer partitions, the upper sums are going to decrease, right? By definition, right? As you take finer and finer partitions, the lower sums are going to increase, right? And because of the integrability condition, the infimum of the upper sums is going to equal the supremum of the lower sums, right? So we call that value the definite integral, right? This thing here is denoted like this. It's called like the upper integral, and then this thing here is denoted like this, the lower integral. So as long as the upper integral and the lower integral equal each other, then that's going to be the value of the definite integral. Okay, so these are just definitions that you've probably seen before. Here's a lemma that's useful. So some of these things I'm just going to state. I'm not going to prove them. Here's something that's quite useful. Suppose you have a function on some interval that's integrable. And I always write integrable like this, integrable. So, yeah, if you look on my door, you'll see, I don't know if you've seen on my door the bingo game, right? So yeah, so BINGOU. Right. This was a game that some engineers at Purdue were playing while I was lecturing, without my knowledge. And it's basically things that I like, things that I say in class, things that I say or do or use in class. And so whenever one of them happened in class, they'd be like, they'd be secretly marking things off, and like, and they were, the instructions to the game, which a student revealed to me afterwards, said that if you get a line, you need to jump up in the middle of class and yell bingo. And nobody did that. Yeah, but anyway, one of the blocks was integrable. This abbreviation integrable, or like CTS for continuous, or it was like disparaging remarks about the TA, or or like mentioning an obscure mathematician. Anyway, so yeah, so yes, you can mark off your bingo block. Integrable. Suppose you have an integrable function bounded by some value b. Okay. I need to wear my reading glasses all the time now. Then here's this is a useful thing. So whenever you have an integrable function, then there exists a sequence of continuous functions. Such that the difference of the absolute value goes to 0. Okay. So as k goes to infinity, if you take the difference between this continuous function and your function, then that difference is going to go to 0. Okay. So in other words, any integrable function can be approximated by continuous functions. Okay. That's actually really handy, because sometimes you don't want to deal with the integrable function, and instead you can get the result for continuous functions, and then say, well, look, I can assume that my continuous functions get arbitrarily close to my integrable function, right? So it allows you to deal with the continuous function in certain cases. Okay, and in fact, one can use step functions in place of continuous functions. And this is simply because any continuous function can be approximated by step functions, right? So instead of approximating your function with continuous functions, you can assume that they are they're step functions. So they're discontinuous, but take on single values in certain intervals. So, yeah. Okay. Okay. Another notion that will show up is something called measure zero. Okay. So, it's sort of like a way of saying small, okay, a way of saying smallness for sets. Okay, so here's the definition. So you have some subset in R, okay, and we say it's of measure zero if we can find a countable family, so if there exists a countable family of open intervals. Right, a countable family of open intervals, I sub k, such that one, E is covered by the union. And two, the sum of the lengths of the intervals is smaller than so if given any epsilon, you can find a countable family of open intervals that covers your set and whose total length is smaller than epsilon. Okay, so you can cover your set with an arbitrarily small family of open intervals. Okay, a set of measure zero. It's actually a really important idea in measure theory. Okay, so to give you a simple example, like of course any countable set is of measure zero. Right. So just to show you, for example, if we think about let's think about the rational numbers in the unit interval, right? So they look like 0, 1, 1/2, 1/3, 2/3, 1/4, 3/4, 1/5, 2/5, etc., right? The rationals in 0, 1 are countable, right? You can make a sequence that hits every single rational in 0, 1. Okay. And so you say, okay, well, those guys are countable. So what I'm going to do is, are they measure 0? You say, oh, sure they are, because somebody gives you an epsilon. Okay, and they say, I want you to cover this set with epsilon material. You say, okay, well, I'm going to cover the first guy with something of length epsilon over 2, right? And then you say, okay, I'm going to cover the second guy with something of length epsilon over 2 squared. I cover the third guy with something of length epsilon over 2 cubed, and so on and so forth, right? And so you can at the end of this process, you've covered every single element of the set with an interval, and the total length of the interval is epsilon. I guess I'm supposed to be less than epsilon, but anyway, you can divide by 2 again or something like that. Anyway, so right, so you can cover every single point in the rationals here, with as little material as you want, which means that they actually take up 0 space, right? In terms of like the thickness of the rationals here, I can cover them. I can cover all the rationals with arbitrarily small length of material, right? So that's what it means to be a measure 0. Okay, and right. So lemma, any countable union of sets of measure 0 is still measure 0. It's still going to be measure 0. And that's you can prove that easily. But in this case, for example, you could see that because we showed it for 0, 1, then we take the union over all of all translates of this, and you see that that Q over the entire line is a measure 0, right? Yeah. Which is kind of shocking to a child, I think, right? Like if you're a kid, you think everything is rational, right? And then you realize that the rational numbers take up 0 space in the real numbers, right? It's kind of shocking. Like 0% of the real numbers are rational, basically. Okay. Yeah, like you can use that to impress like non-mathematical friends. Yes, Kai?
I was going to ask, because Q is countable, why can't we play like the same game?
You could just do it from the start.
Okay.
Yeah, that's fine. Yeah. Okay. So here is a theorem, relating the two, measure and integral. Here's a theorem about integrable functions. It's often called Sard's theorem. So a bounded function is integrable if and only if its set of discontinuities is of measure 0. Okay, so just a way of checking. So basically, right, integrable. If you're an integrable function, you're a continuous function with a set of discontinuities that are only of a set of measure 0. Okay. Okay, so those are the those are the things that I want to get from the appendix right now. There are other things that are other ideas from you know an initial course of analysis that are important. There are, I think, roughly speaking, they fall into three categories: pointwise convergence, uniform convergence, and then the last is something called Fubini's theorem. So let me make sure that I get Fubini's theorem. So I'm gonna give Fubini's theorem first, even though it's last on my list here. This is a theorem that would come in very handy. If f is a function, actually there's some condition on it called measurability, but we're not going to talk about that. So if f is a measurable function such that the double integral of its absolute value is finite, then one can reverse the order of integration without changing the value. Okay, so you can change, instead of integrating with respect to dx and then dy, you could integrate with respect to dy and then dx. So not true in general. Right, like without this condition, you can have functions that where you change when you change the order of integration, then the value changes. There's an example in the red book of Rudin, Rudin's real and complex analysis, for people who are interested. Okay, so let's go backwards. Pointwise convergence. I hope people remember what pointwise convergence means. Right? You've got a bunch of functions, say on some set. It could be in some metric space. So you have some functions. Some complex value functions, say. E is in some subset of a metric space. Say. Then if the limit exists, call it f of x for each x in E, then we say f sub n converges to f pointwise. Okay. So pointwise convergence. Right. In terms of epsilon language, that means that for each point x, for each epsilon you're given, there exists a value that depends on epsilon and also on x, such that the distance between f sub n x and f of x is smaller than epsilon for all n greater than that n. Right? It just means that you have some set. Here's some value f, right? Here's some function f, and what it's saying is that whenever you take a point x and you take an epsilon, so like you take some distance epsilon, then your functions are going to get within that epsilon neighborhood at that point, right? So, whatever epsilon. So for a fixed x, for a fixed epsilon, there's a time past which the values at that point get inside this range, right? That's pointwise convergence for each point that happens. Okay, and then sort of like the better version, the one that's going to be more useful to us, is so-called uniform convergence, right? So again, you have the same setup, right? So you have some function. And you say, well, the phrasing is a little different now. You say for each epsilon greater than 0, there exists an n dependent on epsilon only, such that if we say f sub n converges uniformly to f if for each epsilon you're given, there's a time past which such that if you're past that time, then the distance between fn and f is smaller than epsilon for all x in your set. Okay. So the picture is different. So here's the picture for uniform convergence, which is you have your function, and then somebody gives you an epsilon, but now that epsilon, you think of that epsilon, so for every point, you think of that epsilon range. You think of that epsilon range. Okay. And it says that, well, here are your functions, the f sub n's, right? Here are the f sub n's, right? And they're converging to this guy, right? And what it says is that given, somebody gives you an epsilon, and then there's a time where every value, where the entire function lies within this tube. Okay, that's the difference, right? So there's a time past which the graphs of these functions lie entirely inside the epsilon tube. Okay, whereas over here, you're not worrying about everything occurring simultaneously, right? Here you're just saying that at every point, you give me an epsilon, there's a time that works for that point. Past that time, the function lies in the tube. but you don't know about the rest, about any other points, right? So in this case, at every different point, you're allowed to have a different time. Okay. Whereas over here, the time must be work uniformly across the entire domain. Okay. So that's the difference: pointwise convergence and uniform convergence. You all probably know it. Okay. So the point is that uniform convergence has a lot of nice qualities that pointwise convergence doesn't have. Things that don't work. So for pointwise convergence, right? So like, even if the f sub n are continuous, so let's say that f sub n converge to f pointwise, right? If the f sub n are continuous, then f is not necessarily continuous, right? You can have continuous functions that converge to something that's not continuous, right? You can have integrable functions that converge to something that's not necessarily integrable. Right. Another bad thing is that that if you're taking the integral, you're taking an integral of pointwise functions, that's not necessarily the limit of the integral is not necessarily the integral of the limit. Okay, whereas if you have uniform convergence, then those things actually hold true. So like, if these guys are continuous, then f is continuous. If the f sub n are integrable, then f is going to be integrable. And the limit of the integrals is going to be the integral of f, right? The integral of the limit. Yeah. So there's some nice qualities. Okay. Okay. Yeah. Well, just one comment. It's still not true that if the functions are differentiable, you still don't have that the limit is differentiable. That was false for pointwise. It's also false for uniform convergence. So that doesn't quite work out. There's a more complicated version that does work out, but you have to put a bit more constraints on it for that to work out. Okay, so. Okay, so yeah, so this notion in particular is going to be really important. Uniform convergence, right? So we'll have functions that converge uniformly, and then we'll be able to do stuff with them. Let me just put up one thing in the last 2 minutes that will be used all the time. Yes. Anybody say anything? No. Okay. Those of you who took the complex analysis course know that the wire stress M-test is everywhere. The wire stress M-test. So this is a test for uniform convergence. A test that guarantees uniform convergence. So suppose you have a sequence of functions. If there exist bounds m sub n such that each function is uniformly bounded by the m sub n. So for all points in your set, if the functions are bounded. So if there are bounds that for each function, okay, then if the sum of the bounds converges, then the sum of the f sub n converges uniformly. Okay. So that's something that that we'll use a lot. We'll get bounds on the function. Those bounds are going to converge. That will ensure the uniform convergence of the series, and then we can use all the properties of uniform convergence on it. Okay. So yeah, that's a really useful thing. Okay. So yeah, that's sort of the crash review of analysis results for this course. And next time we'll get into chapter 1. Okay. So chapter 1, like I said, I don't really like chapter 1, but we'll go through it. It's sort of like a motivation, kind of a bit hand-wavy chapter. But it will sort of motivate why we care about Fourier series, and then we'll go into chapter 2 and do the actual Fourier series.
Are we expected to read for Friday class?
Yeah, I think so.
Okay.
Well, you can if you want. So you see, I'll be doing pages 1 through 11 on Friday. You can look at it, but it's not that important. Yeah.
Sounds good.
Yeah.
Thank you.
Yeah. Sure. Okay, good. So yeah, I'm excited. I hope you guys have a fun time this semester. I'm gonna enjoy it. I hope you guys enjoy it. What?
Are you going to enjoy more than complex analysis?
Oh, yeah.
Like about 100 times more.
Yeah, this is proper stuff.
For real.
Yeah.
Yeah. I mean, I like complex analysis, but this is, for me, this is really fun.